I know that we have an exciting NASA night coming up, so I will make sure I end my talk on time. And my name is Peter Chi. In the next 15 minutes, what I would like to report is our recent findings of ion cyclotron waves at the moon, and what these kind of waves can provide hints to the plasma conditions at the moon, and also the exospheric particles around the moon. Okay. Where should I point? Oh, way back there. Okay, great. Okay, so in another life of mine, I study magnetic field fluctuations observed by a large number of ground-based magnetometers and also the Earth-orbiting satellites. So there's one day several years ago, an idea came to me that perhaps I should take a look at the magnetic field measurements at the moon, both on the surface and also by the satellites orbiting the moon. So, and the best data set I was able to find is from the Apollo missions in the 1970s, because the missions had the observations both at the surface of the moon and also by orbiting satellites. Perhaps the orbiting satellites were less familiar to people, but for there are two missions that they're orbiting satellites to provide supporting measurements to the surface package of Apollo mission. And I think the more I study it, the more I appreciate the accomplishment that this mission has done. And that's probably the only surface data set that is available to us, or that they're accessible to us at this moment. But when I try to understand what the data show to us, then I realized that they were stored in a very obsolete format, and actually it took us a long while to be able to restore the data. But after some tedious work in data restoration, we were finally able to study the magnetic field data from both orbiting satellites and also from the lunar surface magnetometers. Well, these are some of the LSM data that we have restored. Now, because my research is focused more on the oscillations or waves in the magnetic field. So one of the first things that caught my eyes was the monochromatic waves seen by LSM. So these are very very nice waves that I've not seen publication reporting about this before. And the wave period is about 10 seconds. Now, and then I try to find a period of time when there were, in fact, two Apollo sites measuring these waves at different locations on the moon. And as you could see, that this is from Apollo 15, and the bottom one is from Apollo 16. So both stations, even they're located at different hemispheres of the moon, they saw similar wave activity. Even though you could see that perhaps at Apollo 16 the wave amplitude is clearly weaker. But also plotted here, there's a black line that shows the local proton gyro frequency. So you can see that the wave frequency seems to be proportional to that particular frequency. And these waves are very nice waves. They're narrow band. Look very nice. So, but and I find that they are in a unique class, which is different from other ion cyclone waves or waves at similar frequency observed at the moon. Now, what I'm showing here are several examples of the waves at similar frequencies reported by different teams, but using wind data, geotail, lunar prospector, and Kaguya. But all of these have a similar condition, that is that they're all observed in the solar wind. But when I found the nice monochromatic wave, they were in fact observed in the Earth's magnetotail. So the difference is that in the solar wind, the typical density is about 7 particles per cc. But our Earth has a magnetosphere which has a tail. Inside the tail, the density is much lower. So there are two parts of the magnetotail. One is near the equatorial plane, we have a plasma sheet which has a density less than 1 particle per cc. But away from the equator, in fact, the density is even lower. So it's actually very difficult to measure it accurately. So you can consider that it's almost like a vacuum there. Now, but first of all, we want to understand what kinds of waves that we're seeing by Apollo LSM. And so we study what you would do, look at the polarization of wave, and we're showing the spectrograms of the ellipticity here and propagation angle. The reason is that we suspect it's ion cyclone waves, and ion cyclone waves have typical properties. I'm showing the 4 well-known properties here, and 3 of them are what you can identify by using magnetic field data alone. For example, you can look at the frequency, you can look at the polarization, and also the propagation angle, which are done here. And we find that the observations of Apollo LSM show consistency with all these properties of ion cyclone waves. So we think they are ion cyclone waves. Now, so why people study ion cyclone waves? In fact, for people who study waves in the Earth's magnetosphere, people study them a lot because these waves interact with particles. For example, particles in the ring current, particles in the radiation belt. So through a study about wave-particle interaction, you understand more about these particles. And sometimes the wave frequencies can provide inference about ion composition. Also, another reason is that these waves are actually found around many objects in the solar system. They have been found near the Mars, near the Venus, near Io, and near the E-ring or inside E-ring of Saturn. And all these places, the waves are associated with the pickup ions. So these are the ionized particles that, because of the I should say flow, that will carry these particles away, and they will form a particular type of distributions that is very unstable. And these unstable distribution will excite waves that we can observe. And then people have found it is actually very powerful use of these observations of waves to infer the amount of pickup ions or the atmospheres associated with these solar system bodies through wave amplitude. So this may be what we could also do with our observations at the moon. But we could tell, well, and then we're trying to find what type of particles are associated with the waves that we have observed. And one way to find the plasma environment at the moon is actually just make use of the magnetic field data by Apollo. The reason is that this is the geometry of a magnetotail. So in the near the equator, there's a plasma sheet, and also you see the field line is coming in toward the Earth, and also in the southern hemisphere is going away from the Earth. So they're in anti-parallel directions. If we look at this Bx in the x direction, you can see that sometimes the x component of the magnetic field will change its sign. That suggests that you can consider that the Earth is crossing the plasma sheet, or the plasma sheet is moving so that you see the crossing at the moon. So, but this was the day we found that there's a large number of ion cyclotron wave events in one day, and in fact, the wave activity seems to be very frequent. It seems like it's very easy to observe them at the surface of the moon, but it is a little, from this it's a little bit difficult to tell that whether or not these waves are also, we're sure that the waves can be observed inside a plasma sheet because of these crossings of the plasma sheet. But it seems like there are some wave events where observed away from the plasma sheet, but we're not sure if they were observed in the tail lobe without much plasma density. So that is something that we still want to work with the Apollo side data team to find out more about the plasma environment. But it seems like the plasma sheet particle can be very important in generating these waves. Another observation that we look at is if you compare waveforms at different sites, you can actually see a phase lag between the two stations. And we also calculate a wave vector using the data, and we find that wave vectors are also different from one side to another. So it seems like, and also, as I said, the wave amplitude Apollo 16 is apparently weaker. So I think these clues seem to suggest that the stronger magnetic field at the Apollo 16 side, which is above 240 nanotesla, could play a role in changing the wave characteristics. So this is actually a very challenging question for a wave person to studying the propagation. But by using two stations, it's probably difficult to tell you the entire story. But let's say if you give me a few more stations, I should be able to tell you what is going on. But I think, in fact, you all understand that we haven't gone back to the moon for 40 years, so I hope that this can happen very soon. Now, okay, 2 minutes. So I think I would want to say that we have started studying ARTEMIS data because ARTEMIS can provide both fields and particle measurements. But it seems like, ARTEMIS has seen several wave events like this, but it seems like it's not as common as in Apollo data because the satellite are orbiting around the moon, and they have to be in certain positions to see these kind of waves. And we find that most of the cases are when the ARTEMIS satellite is in front of the moon toward its sunward side, and Andrew Poppy and colleagues have done a study showing that there are also higher frequency waves observed during this event. This is the ion cyclotron wave events and the few lines are connected to the surface of the moon. So these have been seen, and we have also been able to use the ion distribution to understand that these are certainly associated with plasma sheet particles, but there might be a loss of particle distribution to excite these waves. But there's also another class of waves that I've found, which frequency is a little bit lower. So I suspect that this is not necessarily associated with protons, but maybe associated with the H2. Even though I am really not familiar with the possible particle species here, but I'm glad that I heard people indicating that the recent discovery of H2 and CO by LRO. But so this is a possibility I would be raising here for further discussion. Okay. So I think I'm okay. All right. I think I'm almost done here. But I think, I was going to mention some generation mechanism, but I think that there seems to be two types of generations that associate with these waves, and both are related to the plasma conditions around the moon. And one of the conditions might provide us hint to the exospheric particles coming from pickup ions. So we hope to study more on these. Thank you.
We have time for perhaps one brief question. If not, thank you again, Peter. Okay. Let's take all our questions. And I believe we're next up for NASA night. I think there might be a minute or two to get